Hello and welcome back to Probability and Statistics. Last time we have discussed probability and statistics, an introduction. Today we're going to discuss counting and sets. Let's have first a recap on probability versus statistics. Probability and statistics are both about random processes. When we say probability, it is logically self-contained. A few rules for computing probabilities, and it has one correct answer. In statistics, it is messier and more of an art. We get an experimental data and we try to draw probabilistic conclusions. And it has no single correct answer. So today, we're going to discuss counting in sets. Our learning goals is first, to know the definitions and notation for sets, intersection, union, and complement. Be able to visualize set operations using Venn diagrams. Understand how counting is used for computing probabilities. And be able to use the rule of product, inclusion-exclusion principle, permutations, and combinations to count the elements in a set. To start off with counting, I will give you first an example. A coin is fair if it comes up heads or tails with equal probability. Let's say for instance, what is the probability of getting exactly one heads in 3 tosses of a fair coin? So the answer is with 3 flips, we can easily list the 8 possible outcomes. We have here the triple T, we have TTH, we have THT, THH, HTT, HTH, HHT, and the triple H. Since we are finding the probability of getting exactly one heads in 3 tosses of fair coins, so after listing 8 possible outcomes, we'll have 3 of these outcomes which have exactly one head. So we have TTH, THT, and HTT based on our 8 possible outcomes. So we have 3 of these outcomes which have exactly one head. So to prove that a coin is fair if it comes up heads or tails with equal probability, let's see this example. So since all outcomes are equally probable, we have, so the probability of one head and 3 flips is equal to number of outcomes with one head, total the number of outcomes. So since the number of outcomes in one head in 3 tosses, so we have 3 over the total number of outcome is 8. So it is 3 over 8. So what is the probability of getting exactly one tail in 3 tosses of a fair coin? So we will also get the probability of one tail in 3 flips. So the number of outcomes with one tail total the number of outcomes in flipping the coin. So the answer will be also 3/8. So that means one head in 3 flips and one tail in 3 flips are the probabilities equal. So that means all outcomes are equally probable. So we can say that a coin is fair if it comes up heads or tail with equal probability. That means a coin is in equal probability. So to prove that, so we can see here in our outcomes, the 8 possible outcomes, we have TTT, TTH, THT, THH, HTT, HTH, HAT, and triple H. So if we count here the number of heads exactly getting one head, so we have here TTH, we have THT, we have HTT. So that's 3. So if we're going to get also the probability of one tail in 3 tosses of a fair coin, so we can also get 3. So we have THH, so isang T, so THH. We also have HTH and HHT. So that means a coin is fair. So because it came up with head or tails with equal probability. So think, would listing the outcomes be practical with 10 flips? So let's test first your intuition. So let's say for instance, we have a deck of 52 cards which has 13 ranks. We have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. And a 4 suits which contains hearts, spades, diamonds, and clubs. So a poker hand consists of 5 cards. So 5 cards, we have 5 cards. A one pair hand consists of 2 cards having 1 rank. So 2 cards having 1 rank and 3 cards having 3 other ranks. So let's say for instance, 2 of hearts, 2 of spades, 5 of hearts, 8 of clubs, and K of diamonds. So we have same ranks, so 2, 2, which has different suits, and we have also 3 different tracks with different suits. So that's the case in this one. So what is the probability of a one pair hand? Is it less than 5%, between 5% and 10%, between 10% and 20%, between 20% and 40%, or greater than 40%? So at this point, we can only guess the probability. One of our goal is to learn how to compute it exactly. To start, we note that since every set of 5 cards is equally probable, we can compute the probability of one pair hand as probability of one pair is equals to number of one pair hand over the total number of hands. So to find the exact probability, we need to count the number of elements in each of these sets. And we have to be clever about it because there are too many elements to simply list them all. We'll come back to this problem after we have learned some counting techniques. Several times already, we have noted that all possible outcomes were equally probable and used this to find a probability by counting. Let's state this carefully in the following principle. So, suppose there are n possible outcomes for an experiment and each is equally probable. If there are k desirable outcomes, then the probability of the desirable outcome is k over n. Of course, we could replace the word desirable by any other descriptor such as undesirable, funny, interesting, and remunerative, and etc. So, can you think of a scenario where the possible outcomes are not equally probable? No, there are some cases or there are some scenario that the possible outcomes are not equally probable. So here's one scenario. So let's say for instance on an exam, you can get any score from 0 to 100. So that's 101 different possible outcomes. Why? That's 101. So can get 0 to 100. So let's say for instance, the range of score is from 0 to 100. So since it started with 0, 1 to 100, that's 100 different possible outcomes. We add the 0, so because we can get 0 in an exam. 100 plus 1, which we add 0, so that is 100 different possible outcomes. So the question now is the probability you get less than 50 equal to 50 over 101? So that is not equally probable. So because we can get the probability of this one is 49 point something, for 49.50. So that's an example of a possible outcomes that are not equally probable. Okay. So we come now to sets and notation. So our goal here is to learn techniques for counting the number of elements of a set. So we start with a brief review of sets. So a set is a collection of elements. We use the following notation: one element. When we say element, we write element X is in the set S. Okay, so we read this as the element X is in the set S. Okay, so that's the element. We also have the subset. We say the set A is a subset of S if all of its elements are in set S. So we write this as A subset of S. Okay? We also have the complement. The complement of A is in the set of element S that are not in A. So we write this as A complement or S minus A. Okay? So we also have union. The union of A and B is the set of all elements in A or B or both. So we write this as A union of B. We have this symbol. Okay? We also have the intersection. The intersection of A and B is the set of all elements in both A and B. Write this as A intersection of B. Empty set. The empty set is the set with no elements. We denote it with this symbol. 0 with diagonal line. So we also have the disjoint. A and B are disjoint if they have no common elements. So when let's say for instance A and B have no common elements, that is disjoint. We write that as A disjoint B, which is it will correspond, we say A intersection of B is equal to empty set. When A intersection of B results to an empty set, that means that is a disjoint set. We also have the difference. The difference of A and B is the set of elements in A that are not in B. We write this as A minus B. Okay, so difference. Later on, I will explain that based on using Venn diagram, so don't you worry. So start with a set of 10 animals. So let's say for instance, we have a set of 10 animals. We have in our set S, we have antelope, bee, cat, dog, elephant, frog, gnat, hyena, iguana, and jaguar. So we'll consider two subsets. Let's say for instance M, which is the animal, which is a mammal. So in set M, the animal is a mammal. So we have antelope, cat, dog, elephant, hyena, and jaguar. In our subset W, the animal lives in the wild. So the animal lives in the wild is antelope, bee, elephant, frog, gnat, hyena, iguana, and jaguar. To represent intersection, we have M intersecting the subset W contains all wild animals. So M intersect W is equals to antelope, elephant, hyena, and jaguar. In union, so M union W contains all the animals that are mammals or wild. So, or both. So we combine the two. So antelope, the result will be antelope, bee, cat, dog, elephant, frog, gnat, hyena, iguana, and jaguar. In complement, M complement means everything that is not in M. Example, not a mammal, M complement. So we have bee, frog, gnat, iguana. So for the difference, we have M minus W means everything that's in M and not in W. So M minus W is cat and dog. There are often many ways to get the same set. Let's say for instance, M complement is equal also to S minus M. We have M minus W is also equal to M intersection of L complement. The relationship between union, intersection, and complement is given by De Morgan's law. Let's say for instance, A union of B complement is equal to A complement intersecting B complement. We also have A intersecting B complement is equals to A complement union B complement. So that's De Morgan law. Later on, we will represent that in Venn diagram. In words, the first law says everything not in A or B is the same set as everything that's not in A and not in B. The second law also is similar. So we come now to Venn diagrams. So Venn diagrams offer an easy way to visualize set operations. So in all the figures, S is the region inside the large rectangle. So here. So L is the region inside the left circle. And R is the region on the right circle. Okay? So the shaded region shows the set indicated underneath each figure. So let's say for instance, we have L union R. So we represented that in that way. You see here L and R is overlapping. So in L intersecting R, we can see that the shaded part is in the overlapping portion. So that's the intersection. In L complement, the only shaded region is the right part minus the overlapping section. So we only get here the right region without the overlapping in the left region. Okay, we have also L minus R, the vice versa of L complement. We have only left without the overlapping and the R portion. Okay, so that's how you present sets and notation and Venn diagrams. We can also prove the De Morgan's law in Venn diagrams. So let's say for instance, L union of R complement. So we get the L complement and the R complement. So if we get the intersection of the two, so we can get the same as this one. So we can get L complement intersecting R complement and L union R complement. So that proves the De Morgan law. Okay, so we also have same with this one. So let's say for instance we have L intersecting R complement. If we get the left complement and the right complement and union this two, we can get the same. So left complement union R complement will be equal to L intersecting R complement. Okay, so that's how you prove the De Morgan's law. So we verify De Morgan's laws for the subset A 1, 2, 3, B which is equal to 3, 4 of the set S 1, 2, 3, 4, 5. Okay, so for each law, we just work through both sides of the equation and show that they are the same. So let's say for instance this one, A union of B complement is equals to A complement intersecting B complements. So right hand side we have A union B is equals to 1, 2, 3, 4, 5. So if we get the A union of B complement, we only get 5. Okay, so in the left hand side, so we have A complement which is equal to 4 and 5. So we have the B complement which is 1, 2, 5. If we get A complement intersecting B intersection of B complement, we only get 5. So that proves the De Morgan law. So the two sides are equal. So in number 2, we have A intersecting B complement is equals to A complement union of B complement. So we have the right hand side, we have A intersecting B, so which is that will be equal to 3. And to prove that, so if we get A intersecting B complement, we will remove 3 from the set, so we'll get 1, 2, 4, 5. So in the left hand side, A complement is equals to 4, 5. We have B complement 1, 2, 5. So if we get the A complement union B complement, we get 1, 2, 4, 5. So that proves the De Morgan's law. Okay, so that's an example of De Morgan's law. So also the two sides are equal. So we come now to products and sets. So the product of set S and T is a set of ordered pairs. So in words, the right hand side reads the set of ordered pairs S and T such that S is in set S and T is in set T. So if we get the product of that set, so we get, so let's say for instance 1, 2, 3, 4 and 1, 2, 3. So 1 times 1, 1, 1. 1 times 2, that's 1, 2. 1 times 3, that 1, 3. 1 times 4, so 1, 4, and etc. and so on. So let's say for instance the set S is 1, 2, 3 and the set T is 1, 2, 3, 4. So if we illustrate that in a diagram here, so we have the set 1 to 4 multiplied, or the product of set 1 to 4 and 1 to 3 is a subset of 0 to 5 multiplied by 0 to 4. So in diagram, we represent that here. So we have here 1 to 4 and then 1 to 3. So as you can see here, this purple this purple rectangle denotes our product of sets. The product of 1 to 4 and 1 to 3 is a subset of 0 to 5 and 0 to 4. So that's the products of sets. So the right hand figure also illustrates that if A is a subset of S and B is a subset of T, then A multiplied by B is a subset of S multiplied by B. Okay? Or the product of A and B subset the product of S and Okay, so we come now to inclusion-exclusion principle. So the inclusion-exclusion principle says the cardinality of A union B is equals to cardinality of A plus cardinality of B minus the cardinality of A intersecting B. So we can illustrate this with Venn diagram. So S is all the dots inside of the rectangle. We have the A is the dots in the blue circle and B is the dots in the red circle. So the cardinality of A is the number of dots in A, and likewise for the other sets. So the figure shows that the cardinality of A plus the cardinality of B double counts the cardinality of A intersecting B, which is why the cardinality of A intersecting B is subtracted off in the inclusion-exclusion formula. So if we're going to count that, if we're going to count this one, so we will deduct the cardinality of A intersecting B. Why? Because it double counts the dots inside this portion. So let's say for instance, if we were going to count all the dots here, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that's 24 total. However, if we will follow this formula, we'll get the cardinality of A plus the cardinality of B. So we will get what? So we count first the cardinality of A. So the cardinality of A is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that's 16. In cardinality of B also, we'll also get 16. So 16 plus 16, that is 32. So if we will count all the dots here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. That's only 24. So 36 versus 24. So that means there is a duplicate. And that is this one, no? This A intersecting B. So that means we will deduct the cardinality of A intersecting B. So we will deduct 36 minus 1, 2, 3, 4, 5, 6, 7, 8. 36 minus 8, that is 24. So in that way, we can get the cardinality of A union of B. Okay, so that is the inclusion-exclusion principle. So to present that in formula, so para mas maintindihan nyo, so let me write that. So the cardinality of A is equal to what? So if we will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So that will be 16. The cardinality of B is equal to also 16 if we will count that. So if we add these two, that will be equal to, if we get the cardinality of these two, so cardinality of A plus the cardinality of B will get 32. Okay? So however, if we will deduct the A intersecting B, so A intersecting B is equal to, so 1, 2, 3, 4, 5, 6, 7, 8. So 8. So 32 minus 8, that will be 24. Okay, so that's how you do the inclusion exclusion principle. We're just removing the double count in the set. Okay, so let's say for instance we have an example here in a band of singers and guitarists. So 7 people sing, 4 play the guitar, and 2 do both. So how big is the band? If we can see the problem here, so we have 7 people sing, we also have 4 play the guitar and 2 do both. We can represent that in inclusion exclusion principle. So let S be the set singers and G be the set guitar players. So the inclusion exclusion principle says that size of band is equal to the cardinality of S union of G, which is equal to the cardinality of S plus the cardinality of G minus the cardinality of S intersecting G. So if we change the value now, if we get the value, so cardinality of S, singers, so we have 7 people singing. We have 4 play the guitar, so we have 4. So 7 plus 4 minus the cardinality of S intersecting G, so we have 2 doing both, so minus 2, that is 9. The size of the band is 9. So that is the inclusion exclusion principle. We also have the rule of product. So the rule of product says if there are n ways to perform action 1 and then by m ways to perform action 2, then there are n times m ways to perform action 1 followed by action 2. So we will call this multiplication rule. We'll also call this multiplication rule. So let's say for instance, if you have 3 shirts and 4 pants, then you can make 3 multiplied by 4, you can make 12 outfits. So think. So an extremely important point is that the rule of product holds even if the ways to perform action 2 depends on action 1, as long as the number of ways to perform action 2 is independent of action 1. So another example, there are 5 competitors in 100m final at the Olympics. In how many ways can the gold, silver, and bronze medals be awarded? So the answer for that is there are 5 ways to award the gold. Once the gold was awarded, there are only 4 ways to award the silver, and then 3 ways to award the bronze. So let's say for instance, we have 5 competitors. If we already awarded the gold, that means we will deduct that one winner. So we have only 4 ways to award the silver. Same with the bronze. If we already awarded the silver, that means we have only 3 ways to award the bronze. So the answer for that is 5 times 4 times 3. We have 60 ways to award the gold, silver, and bronze medals. Okay, so that's how you use the rule of product. Let's come now to permutations. When you say permutation, a permutation of a set is a particular ordering of its elements. For example, the set ABC has 6 permutations. We have ABC, ACB, BAC, BCA, CAB, and CBA. We found the number of permutations by listing them all. You could also have found the number of permutations by using the rule of product. That is, there are 3 ways to pick the first element, then 2 ways for the second element, and 1 for the first. This gives us a total of 3 multiplied by 2 times 1, so which is equal to 6 permutations. In general, the rule of product tells us the number of permutation of a set of k elements, which is k factorial is equals to k times k minus 1 until 3 times 2 times 1. We also talk about the permutations of k things out of a set of n things. We show what this means with an example. Let's say, for instance, we list all the permutations of 3 elements out of the set A, B, C, D. the answer would be a longer list. We have ABC, ACB, BAC, BCA, CAB, CBA, and so on and so forth. We note that ABC and ACB will be counted as distinct permutations. That is, for permutations, the order matters. There are 24 permutations. Note also that the rule of or product would have told us there are 4 times 3 times 2, which is equals to 24 permutations without bothering to list them all. In contrast to permutations, in combinations, order does not matter. Permutations are lists and combinations are sets. I will show you an example of what that means. Let's say, for instance, we list all the combinations of 3 elements out of the set A, B, C, D. The answer would be such a combination is a collection of 3 elements without regard to the order, so A, B, C, and CAB both represent the same combination. We can list all the combinations by listing all the subsets of exactly 3 elements. So the answer would be ABC, ABD, ACD, and BCD. Okay? There are only 4 combinations, contrast with 24 permutations in the previous example. The factor of 6 comes because every combination of 3 things can be written in 6 different orders. So let's come now to the formula of combination and permutation. We will use the following notations. N permute K, which is equal to the number of permutations or list of K distinct elements from a set of size. We also have N choose K, which is equal to N over K, which is equal to the number of combinations or subset of K elements from a set of size N. We emphasize that by the number of combinations of K elements, we mean the number of subset of size K. And these have the following notations and formulas. So for permutation, we have N pk is equals to N factorial over N minus K factorial, which is equal to N multiplied by N minus 1 until N minus K plus 1. For combination, we have N choose K is equals to N factorial divided by K factorial multiplied by N minus K factorial, which is equal to N permutation of K over K factorial. So we can illustrate the relationship between permutations and combinations by lining up the results of the previous 2 examples. For permutation, we have 4p3, we have the longer list ABC, AC, BBAC, and so on and so forth. For combination, we have this 4 subsets. So we notice that each row in the permutation list consists of all 3 factorial permutations of the correct corresponding set in the combination list. So what I mean by that is each row will consist of 3 factorial permutations of the corresponding set in the combination of list. So let's say, for instance, ABC, ACB, BAC, BCA, CAB, CBA. So when we get the distinct elements here, we'll get ABC. In the second row, we have ABD, ADB, BAD, BDA, DAB, and DBA. The distinct elements there is ABD. Same with the other row. So let me give you an example. We'll count the following. For number 1, the number of ways to choose 2 out of 4 things, which order does not matter. So the answer for that is it is asking for combination. So which is equal to 4 over 2, which is equals to 4 factorial divided by 2 factorial multiplied by 2 factorial, which is equals to 6. How come that it resulted to 6? So let me write something here. So let's say, for instance, we have 4 times 3 times 2 times 1. divide it by 2 times 1 multiplied by 2 times 1. Okay? So, to get the result, we simplify the equation. So, we cancel this one and this one. So, it will result to 4 times 3 divided by 2 times 1. So, it will result to what? 4 times 3, it's 12 over 2. So, the answer is 6. That's how we manage to get the result 6. Okay, so we simplify the equation. So the second problem, the number of ways to list 2 out of 4 things. This is asking for permutation. So we have 4 permutation 2, so which is equal to 4 factorial divided by 2 factorial, which is equals to 12. Okay. So if we compute that, so we have 4 times 3 times 2 times 1. Okay? Divide by 2 times 1. So if we simplify the equation, we cancel this one, we will result to 4 times 3 is 12. Okay? So that's how we manage to get the result. For the third problem, we have the number of ways to choose 3 out of 4 things. This is also asking for combination. So same with number 1. We have 10 over 3. We have 10 factorial over 3 factorial multiplied by 7 factorial. We simplify the equation. In 10 factorial, we cancel 7 factorial and 7 factorial. We only have 10 times 9 times 8 over 3 times 2 times 1, which is equals to 120. Okay? So, hope you understand using that example. So, another example, let's say for instance, we'll count the number of ways to get 3 heads in a sequence of 10 flips of a coin. This asks for the number sequences of 10 flips, the heads or tails, with exactly 3 heads. So that is, we have to choose exactly 3 out of 10 flips to be heads. So this is the same question as in the previous examples. We have 10 over 3 is equals to 10 factorial divided by 3 factorial times 7 factorial. We simplify the equation. So we cancel out 7 factorial, which results to 10 times 9 times 8 over 3 times 2 times 1, which is equals to 120. For number 2, if the coin is fair, what is the probability of exactly 3 heads in 10 flips? So each flip has 2 responsible outcomes, heads or tails. So the rule of product says there are 2 to the 10th, which is equals to 1024 sequences of 10 flips. Since the coin is fair, each sequence is equally probable. So the probability of 3 heads is, so 120 divided by 1024, the probability is 0.117 or 11.7%. Okay? So that's it for counting and sets. So hope you understand our lesson for today. So see you next week for another lesson. For any question, don't hesitate to send me a message on my email or paste it on our discussion board. See you next time. Thank you.